Hi everyone, and welcome back to our new episode. I'm happy to welcome Haya today. Welcome, Haya.
Hi, I'm happy to be here and I'm excited to talk to all of you today.
Honestly, I'm super excited to have you here as a speaker, so it was awesome. I saw your blog post that was just got all my attention, my interests, so it was just you, which came up with a fascinating subject, I would say. Welcome again for anyone who's just joining, and for everyone who is just new to the episodes. A quick explainer how that all works, because as you can see, there's a navigation bar easily accessible for you. There's a Q&A icon there, so anytime you feel, I have a questions, I would like to raise the question, please feel free to ask. There's no silly question at all. We're just happy with everything which comes from your side. So it's always cool stuff in the community. We talk freely. Hiya, so where are you based?
I am based in Toronto.
Toronto, that's awesome. I think we never had someone from Toronto yet. So the first one, welcome.
Oh, that's exciting.
What are you doing professionally speaking? So what are you doing on a daily basis?
I'm working as a data scientist. I'm actually consulting with the World Bank at the moment on a couple different projects. I really enjoy it because the work is always challenging and it's something different, and it's an interesting way to use data science outside of the corporate world.
Oh, I can imagine, definitely. Was it also your educational background, so data science?
So I'm actually completely self-taught. I did an undergrad in biology because I had plans to be a veterinarian. I went a different way on that and tried a bunch of different things. And I sort of discovered that I really enjoyed coding. And from there, I discovered what machine learning was, and I just fell in love. It's really exciting for me to like see the new developments that happen almost every day. I think I've kind of found the thing that I can see myself doing for a very long time.
Awesome. So once you're addicted forever, right?
Pretty much.
So before we talk about why you actually have that interest in that subject, I would like to start a little poll at the moment, so that helps us to get a better understanding who of you guys is listening and what you're doing. This will help us to have a closer look at how we can focus the presentation, at least not me, but Haya, of course. And for me, it's also interesting to see how we can help you to make it more fruitful for you to listen. But Haya, so since we're just watching for people to answer the two questions about what level of knowledge and what kind of profession we have, coming back to the initial subject about causality and NLP, what the heck? Why did you choose, or why are you so interested in causality?
I'm interested in causality because I feel like I've spent my whole life asking the question why. And it was only relatively recently that I discovered there's an entire math around it, in which case I'm talking about econometrics, which I think of as like the fun part of economics. I became very fascinated with the idea that we could actually try to derive what cause was. And I started thinking more about that. But because I'm also very much into machine learning, and in particular NLP, I was very much interested in actually how to do causal inference using NLP techniques. So it was actually the sort of reverse relationship that brought me to this topic. It got me started to thinking about, well, what about the opposite direction? How could causality be used to improve NLP? So,
yeah, that's interesting. And you have made, of course, 2 blog posts or more blog posts already. At least I know of 2 of them.
Yes, there are 2 thus far. I do have another one planned in the works, but it's a little bit tricky. So we'll see how that goes.
Okay. So we're just excited to see how you progress here. So the poll is over. I think nearly everyone has answered. So let's time to share the results. As you can see, yes, we have, yeah, of course, a lot of data scientists here, but project management is also not little. Hey, so for everyone who just say I'm Ava, please be Hannah. Don't worry because I don't mention what you're doing. It's also just for me good learning. So if you put what you do, your job actually in the chat, that would be nice. It's just a learning. I see a lot of people in the space and looking at the level of knowledge on NLP. Yes, we have a lot of people just new to it, but that's also interesting. It's a split 50-50%, nearly split to novice and advanced. I think that's probably a challenge to address both of them. But again, feel be invited to ask the questions. So if you think I'm dropping from the chair, so I didn't really get what's happening here, just ask, don't worry. I'm happy about any kind of question. I think I was also very pleased to answer them. Okay, so just stopping the poll now. Thanks again for answering it. Yeah, so I mean, I know you made put a lot of work in the presentation. You sent it already to me, that was fine. And so we have a lot to talk about. So take the floor, it's yours.
Okay, I'll just get started then. So, hi everyone. Today we are going to be chatting about how causality can be used to improve NLP models. I'm going to go ahead and share my screen so we can look at this together.
Yes, we can see it. Perfect.
Okay, great. So I would like to start today with a quote about bias in AI from Catherine Hume at Borealis AI. She says, algorithms are like convex mirrors that refract human biases, but do it in a pretty blunt way. They don't permit polite fictions like those that we often sustain our society with. She actually continues by adding, we need to be careful because if we don't design these systems well, all that they're going to do is encode what's in the data and potentially amplify the prejudices that exist in society today. So this quote directly reflects what sparked my interest in applying causality to NLP models. And while today's conversation will be specifically focused on the practicalities of how to improve NLP models, I felt that it would be good for us to start by reflecting on why this topic is important to us. Personally, I continue to be concerned about how the tools that I use as a data scientist, how they're flawed in ways that are both difficult to interrogate and therefore they are difficult to change. As AI practitioners, I'm sure that many of you can relate to my concerns, and perhaps for some of you, these are issues that you face daily.
I think definitely if you think about the whole discussion around transparent AI, so yeah, sure, we need to be fully aware of what's happening, and looking at the stakeholders, we have to tell them what's happening as well. Fully agree with what you're saying. Thank you.
So full disclosure, I have a tiny obsession with causality. So I was very excited when I read a survey paper by NLP researchers that covered the recent literature connecting causality to NLP. I have shared a link at the end. There were many interesting takeaways, but most relevant to our conversation today was how causality could be used to improve NLP models. So I'm happy that I get to share with all of you some of what I have learned. This talk is split into 5 sections. First, an introduction. That will be followed by an overview of causality. And the final 3 sections deal with improving specific aspects of NLP models, robustness, fairness and bias, and explainability. I will be using case studies for examples, many of which will be NLP related. I will also reference literature where relevant, but all the citations are shared at the end for those of you who wish to do some follow-up reading. So also just feel free to ask questions. My hope is that this talk will feel like a casual conversation. So Firstly, why should we be interested in NLP, or more specifically, AI language models? Well, every day we are interacting with products that are built with NLP. We rely on the internet and search engines to answer all of our questions, which means we are relying on NLP. For instance, Google search is powered by an AI language model named BERT, and Microsoft Bing uses OpenAI's GPT-3 to suggest better autocomplete recommendations. Without diving too deeply into how these two models I've named were created, it is relevant to note that these models rely on adaptations of the transformer architecture that was introduced back in 2017. However, it was only last year that Google announced that they were using BERT for 100% of search queries. Around the same time, Microsoft revealed that they were using their access to OpenAI's GPT-3 to improve Bing. The progress made in natural language processing over the last 4 years is stunning, and the change has been revolutionary for both businesses and researchers. Progress always has a cost, however, and in this case, the costs include how these powerful NLP models harbor bias towards certain historically marginalized groups. The implications of this bias is discussed thoroughly in a book that I highly recommend by Safiya Noble called Algorithms of Oppression. In this work, she covers how search engines we use reinforce racism. The theoretical details of how exactly bias is encoded is actually explained very well in OpenAI's paper that introduced GPT-3. And details about the bias in Google's BERT is discussed well in a paper contributed to by AI ethicist Timnit Gebru. I encourage people to check that one out as well. Bias aside, companies have other motives for wanting to improve NLP models. The other two prevalent issues are robustness and explainability. Often, models used in the real world have vulnerabilities related to generalization. So a model can test well during development and perform poorly in deployment. Secondly, NLP models like the ones we are discussing today are often criticized for being black boxes where their inner workings are completely opaque. This raises serious concerns in fields such as healthcare, where trust is paramount. Because how can we trust tools we cannot explain? We're also increasingly reliant on machines to help us make everyday decisions. We turn on Google Maps and we expect that it will tell us the best route to take. If Google Maps is wrong, then the worst outcome is that we are late. Other decisions have higher stakes. For instance, since we're talking about NLP, imagine a model trained to rank candidates by their resume. Imagine losing out on job opportunities, which means losing out on opportunities for better quality of life, simply because the model is biased against female applicants. Is the model sexist? Well, it would have been trained on historical data where successful candidates are predominantly men. So the model learns that being male is a predictor of success. If this model is sexist, it is because society is sexist. Acknowledging that there is a problem is an important first step. And I know that everyone who chose to attend today's talk has already taken this step. So where to next? My answer to that is causality. What exactly is causality and why should we think about it? To me, causality is simply cause and effect. It is the question why. For a wonderful introductory book to causality, I suggest checking out Judea Pearl's aptly titled The Book of Why. Traditionally, machine learning relies on pattern recognition and is focused on prediction. However, these predictions are the result of correlations, which, as the saying goes, does not imply causation. Causal inference, however, is difficult because determining cause requires eliminating all other possibilities or confounders and imagining what would happen if the cause were removed. Normally, we would conduct randomized trials like in medicine so that we can be sure that the treatment does in fact cause the outcome and is not merely correlated. So the next section will be an overview of causality so that we can better understand how to apply this concept to NLP models. So this overview of causality, it's by no means comprehensive, but it should serve as a general introduction to the concepts that will help us improve NLP models. This section will cover 4 broad concepts and then connect them with an NLP case study. The 4 concepts are counterfactuals, potential outcomes, spurious correlations, and causal graphs. When we think about causality, it is necessary to think about counterfactuals. Everyone at some point has wondered what would have happened if we had made different choices. We imagine what our lives could have been in an alternate reality, supposing we had made this different choice. Let's say that in school, you had the choice of music or art. You chose art and you learned the basics of color and design, and later these skills were helpful in your marketing career. Here, the treatment is a binary choice between art and music. You had to pick one and you could not choose both. But what would have happened if you had chosen music? Now we are imagining the counterfactual. Supposing you had a time machine and could go back to the point and intervene on that choice, changing your choice to music. In the language of causality, this would be an intervention. Interventions are key to causal inference. They are necessary since we must define counterfactuals based on an intervention of interest. But what exactly do I mean when I say intervention? To show that a treatment actually causes an outcome, a change in treatment should cause a change in outcome, while all other exogenous variables, which we will refer to as covariates, are kept constant. It is specifically this type of change in treatment that is referred to as an intervention. More formally, this is called the ceteris paribus assumption regarding exogenous variables. We are assuming that all covariates remain at their original values when we change the treatment. So then the causal effects are defined as the magnitude by which an outcome variable is changed by a unit level interventional change in treatment. This can be simplified as the difference in outcomes between the real world and the counterfactual world. As seen in this image, in the real world, t equals 1, or the treatment is applied, and in the counterfactual world, t equals 0, or the treatment is not applied. In this case, the causal effect of interest is the average treatment effect, or ATE, and it describes the relationship between a factual observation and its counterfactual. It is essentially the difference in potential outcomes. The fundamental problem of causal inference is that it is impossible to directly observe a counterfactual outcome. It is essentially a missing data problem. This is something that economists and philosophers have puzzled over for a very long time. For a methodological approach, today we will be discussing the potential outcomes framework that is attributed to Imbens and Rubin. Notably, Imbens and Angrist, another economist, were recently awarded the Nobel Prize in Economics for their work on developing methodology for causality. I mentioned this because Angrist is one of the authors of a book titled Mostly Harmless Econometrics, and I have to highly recommend it because it served as my introduction to causality. Returning to potential outcomes, it is a framework.
Yeah, just a quick question, because you mentioned a lot of literature, and which is cool books. will it be, do we get
Yes.
a kind of list in the end or so?
Yes, I've listed everything's hyperlinked and listed at the end, all the resources, every single piece of literature or book that I reference will
Good.
be there at the end.
Perfect.
Yes, I do reference quite a few books because I'm a fan of books, but hopefully they're all relevant.
That's cool. Thank you.
So returning to potential outcomes, it is a framework that describes a statistical model of cause and effect with counterfactual conditionals. These are statements that would be true under different circumstances. To simplify, one potential outcome is that the treatment is applied, and the other potential outcome is that the treatment is not applied. The potential outcome framework also specifies several assumptions that need to be satisfied for causal inference. Today, we will be briefly discussing 3 of these assumptions: ignorability, consistency, and positivity. Ignorability requires that the treatment assignment be independent of the realized counterfactual outcomes. This is usually accomplished with random assignment. However, when using observational data, this may not be feasible or ethical. In such cases, it is necessary to rely on conditional ignorability. This, however, requires a strong assumption that there are no unobserved confounders. Confounders cause spurious correlations, and I will discuss them later. Ignorability essentially means that we can ignore how an individual ended up in one versus the other group when it comes to calculating potential outcomes. For instance, we can ignore how a student would end up choosing art or music when we're calculating the potential outcomes. In other words, there can be no omitted variable bias. So the next assumption is consistency. This requires that the observed outcome at a given treatment status for a given unit is the same as would be observed if that unit was assigned to the treatment. This assumption of consistency can also be referred to as the stable unit treatment value assumption, or SUTVA. To simplify all of that, the consistency assumption makes 2 assertions about the relationship between counterfactual outcomes and the observed ones. First, that there is no interference, such that the outcome for a unit is affected only by its treatment status and not the treatment status of other units. Second, there is only one version of treatment. So returning to our art music example, a student's choice to take art or music should not depend on what other students choose, and there is only one choice to be made: art or music, not both and not none. Another way of thinking about consistency is that it assumes there are no spillover effects. Lastly, we have the positivity assumption. So this is the assumption that the probability of receiving treatment is bounded between 0 and 1. We need to be able to observe units that have the treatment, as in t equals 1, and units that do not have the treatment, t equals 0. Positivity also implies that the treatment status cannot be perfectly predicted given the covariates. So, for example, we need to be able to observe students who chose art, and we need to be able to observe students who chose music. Furthermore, we should not be able to perfectly predict their choice if we knew all exogenous factors like height or race. As promised, we will be discussing spurious correlations and confounding in greater depth because it is essential to understanding the difference between a correlative predictive model like BERT and a causally motivated approach. So firstly, not all spurious correlations are confounders, but all confounders lead to spurious correlations. For example, imagine we were trying to show a causal relationship between smoking and poor health outcomes. People who smoke also often chew gum. So if we were to regress poor health outcomes on chewing gum, we might get a significant coefficient indicative of a positive relationship. However, this would clearly be a spurious correlation because chewing gum does not cause poor health. Confounders, on the other hand, are different because they have an effect on both the treatment and the outcome. A confounder in our smoking example would be diet or exercise. Both have an effect on the outcome of poor health, but they also have an effect on the treatment. To unpack this, consider that a bad diet full of sugar will affect mental acuity, which may cause a person to smoke more frequently to stay sharp. Simplistically, confounding occurs when a variable or a confounder has an effect on both the treatment T and the outcome Y, causing a spurious correlation. So this relationship is shown here, where W is the confounding variable. Let's think about an NLP example. For instance, we could be interested in determining if the politeness of an email has a causal effect on the response time. Here, the treatment is whether an email is polite, and the outcome Y is the response time. W represents the textual features of the email that could have a confounding effect on both the treatment and the outcome. Such a textual feature could be the topic. If the topic is an emergency, perhaps the email may not be polite due to haste, and in the case of an emergency, the response time would be prompt. Therefore, the text W is spuriously correlated with both the treatment and the outcome. It is acting as a confounder. For our purposes today, we will be talking more broadly about spurious correlations, but it is important to keep in mind the particular case of confounders. So causality can be difficult to conceptualize. Therefore, it just helps to draw causal graphs, or as they are called, directed acyclic graphs, acronym DAG. In the introduction, I mentioned a book titled The Book of Why by Judea Pearl. It was Pearl who is the computer scientist who actually made DAGs popular for explaining causality. A DAG, or causal graph, is a graph that has direction as indicated by the arrows, and it must be acyclic, as in there are no feedback loops or cycles. This last part is important for being able to determine causality. Consider the following example of a feedback loop. The first econometrics research paper I read looked at the effect of Israeli checkpoints on Palestinian employment. In this scenario, the author Abrahams was evaluating the impact of checkpoints deployed by the Israeli army on Palestinian roads, but there were many potential confounding factors. For instance, violence in Palestine could lead the Israeli army to deploy checkpoints, and more checkpoints in Palestine could lead to greater unemployment for Palestinians. But then a higher unemployment rate in Palestinian towns could lead to more violence in Palestine. Here we have a cycle or feedback loop. It becomes impossible to distinguish causal effect because we will never be able to determine whether it was the Israeli checkpoints or the Palestinian violence that was causally affecting Palestinian employment. So Abraham's solution was actually to use a clever instrumental variable, and I've linked the paper at the end for anyone interested. Returning to DAGs, in graph terminology, a DAG has vertices and edges, where each edge is directed from one vertex to another without forming a closed loop. It is necessarily acyclic. Again, no feedback loops. Consider this causal DAG. Here, the treatment T could be the quality of a text or an email, for example, whether it is polite, and Z represents the potentially confounding qualities of the text, such as topic or writing style. The directed arrows from T and Z can connect to the text, which is denoted here as W. And notice that the bidirectional arrow between T and Z indicate that they are correlated. So then the directed arrow from the text W to the outcome Y, this is how the treatment T affects the outcome Y. Here, X represents other covariates, such as the time of the email or the subject line. In this causal graph, changing the value of the treatment T might change the distribution of the outcome Y. We can think of the arrow from T to W as representing the true causal effect, and the arrow from Z to W as representing a spurious correlation, since Z is a confounder. So thank you for bearing with me as we went through those 4 concepts. Now that we've covered counterfactuals, potential outcomes, yes?
Just to clarify, it is a spurious causality means it's not really a causality between two variables, right? We just think it could be.
Yes, it's how I was mentioning that you know, if you regress poor health outcomes on chewing gum, it might seem like chewing gum has something to do with that, but really it's a spurious correlation. There's no actual relationship there where chewing gum has a causal effect on poor health outcomes. Does that help?
Yeah, sure. And if you look at those kind of relationships, or analyzing those kind of relationships from a causality point of view, do we need other science like social science to model that relationship between variables, or can we do that from the data point of view? What's your opinion?
So actually, this kind of causality, this kind of spurious correlation thing that we're dealing with, it extends way beyond social science. It's something that's used very much in medicine. For example, epidemiology or any kind of clinical trial, they care a lot about making sure that they really understand what is causing things. So this like idea of spurious correlations is found beyond the social sciences. In fact, it probably is a tricky thing to deal with in physics as well, I would assume.
Thank you.
So now that we sort of went through some of those concepts, I was thinking we can connect these ideas in a case study that can highlight how we can use causality to improve NLP. This particular case study comes from the survey paper mentioned in the introduction. So consider a scenario where we want to build a classifier to predict a diagnosis or medical condition given a written clinical narrative and using a labeled training set from multiple hospitals. So this example is shown in this image where Z represents the hospital, Y is the physician-assigned diagnosis label, W is the written clinical narrative, and Y hat is the prediction from the classifier. Essentially, the classifier Y hat takes the text of a clinical narrative, W, as input and outputs a diagnosis prediction. However, the written narrative is also based on the physician's diagnosis and is also influenced by the writing style used at Hospital Z. In this case, we want to intervene upon the Hospital Z while holding the label Y fixed. Counterfactually, we would set the hospital to a different hospital, which gives us a counterfactual clinical narrative from that hospital, while Y, the diagnosis label, still is held fixed. So then, given the input of a counterfactual narrative, our classifier Y hat should output what would be a counterfactual prediction. Since the training data has records from multiple hospitals, there could be a hospital where a patient is more likely to be diagnosed with a particular condition. It could also be possible that the doctors at a specific hospital tend to use unique writing styles based on that hospital's practices. For example, they could use different acronyms. Now, if we were to just go ahead and build a correlational predictive model using BERT, this predictor would use textual features that carry information about Hospital Z, which happen to be useless for predicting diagnoses within any particular hospital. Therefore, the challenge here is in poor out-of-distribution performance, and that is due to the spurious correlation between writing style and medical diagnosis. Predictions will not be valid for hospitals outside the training data. In this particular scenario that we're looking at, two conditions must be met for a spurious correlation to arise. First, in the training data, there needs to be a factor Z that is informative about both the features X and the label Y. And second, Y and Z must be dependent in the training data in a way that is not guaranteed to hold in general. In this medical diagnosis classifier example, as seen in the causal graph, Z is correlated with Y. This spurious correlation between the hospital Z and the label Y exists within the training data. Therefore, a predictor will learn the parts of X that are informative of the hospital Z. However, this predictor is not robust because the learned relationship between the features X and the label Y will not hold during deployment. Now that we've gone through an overview of causality, we're ready to start applying these concepts to NLP. And when I talk about improving NLP models, I'm focusing on improvement along 3 dimensions. That is robustness, fairness, and explainability. Starting with robustness, what exactly does it mean for a model to be robust? Well, for us, it means that a model should be able to generalize well when given inputs that are different from the training data. In our medical diagnosis classifier, this would mean testing the model on data from hospitals that were not included in the training data. As explained, such a model would not generalize well to this novel data, and therefore it's not robust. Models in production need to be robust to the variance of real life. In practical terms, if a model is trained to diagnose anxiety based on clinical reports, if the data is homogeneously white, then if used for Black patients, it would fail to accurately predict anxiety in these Black patients. However, if this model was trained on racially representative data, but only from a single hospital, then if used on patients at other hospitals, again, this model would perform poorly. In general, an early lesson of machine learning is that overfitting to the training data leads to poor generalization. However, as we know, there are several ways that a model can fail to generalize. What we are interested in specifically is how causality can be used to address the issue of spurious correlation. Research has shown that AI language models are often right for the wrong reasons, and they will make errors in out-of-distribution settings due to their reliance on fallible syntactic heuristics, which we can think of as spurious shortcuts. Sensitivity and invariance tests are a way of testing for robustness, and there are several approaches to learning predictors that can pass such tests. These approaches are ways of incorporating domain knowledge of the causal structure of the data into the learning objective, which means they are causally motivated approaches. Today, I will just be covering one such approach, counterfactual data augmentation. But before we do that, let's discuss how exactly sensitivity and invariance can be used to increase robustness. When dealing with AI language models like BERT that rely on correlations for predictions, it's essential to ensure that the predictions are not right for the wrong reasons. There are 2 types of evaluations that can be used for this task: invariance tests and sensitivity tests. Invariance tests assess whether predictions are affected by perturbations that are causally unrelated to the label. Sensitivity tests apply perturbations that should, in some sense, be the minimal change necessary to switch the true label. The purpose of a causally motivated invariance test is to see whether a predictor behaves differently when given counterfactual inputs. If Z is the label of a cause in the text that should be causally irrelevant to label Y, then a counterfactual input would be a sample where Z is set to its counterfactual, as in Z becomes not Z. Research has shown that a model whose predictions are invariant across such counterfactuals can in some cases be expected to perform better on test distributions with a different relationship between Y and Z. So sensitivity tests are similar to invariance tests in that they're also evaluations of counterfactuals. However, the difference is that the label Y is changed, but all other causal influences on the sample are held constant. So the counterfactual of a sensitivity test can be expressed as a sample where the outcome label is set to its counterfactual, as in Y becomes not Y. At this point, I'd like to link these two concepts back to economics, which is a field that cares a great deal about testing rigorously for sensitivity and invariance. So in a basic regression setup, we regress the outcome Y onto the treatment T. Assuming that we get a significant regression coefficient, this is still not enough to claim causality. So economists will add as many potential confounders as they can to the regression as controls to show that the coefficient does not change much with their inclusion. So this is testing for sensitivity with robustness checks. And if the coefficient does not change more than, for example, 1 standard deviation, once the controls are added, then we can say that the coefficient was invariant to the changes. So for an economist at this stage, the results when presented will not be dismissed out of hand, but nonetheless, it will still be an uphill battle to convince other economists that there was a causal effect. Luckily, for our purposes, we're not trying to prove causality. Rather, we are trying to use causally motivated approaches that rely on the concepts of sensitivity and invariance to improve our models. So one of these approaches is to utilize counterfactual data augmentation, and this is what we will be discussing next. So the reason I chose to focus on counterfactual data augmentation is because it's a versatile way to improve robustness, fairness, and explainability in NLP models. It is also the most accessible technique. I'm sure many of you have experimented with data augmentation, so this can serve as an extension of a technique that is familiar to NLP practitioners.
A quick question regarding the wording. So counterfactual, can you explain again what counterfactual actually means?
So imagining what would have happened if a different choice had been made. So if the factual observation is that the treatment is applied, then the counterfactual observation would be what would have happened if the treatment was not applied.
And thinking about counterfactual data augmentations, the term a phrase you're just using here, can you give an example again what that means?
I'm actually going to go into that when I talk more about how exactly to do counterfactual data augmentation, because the specific cases of how it can be used to address, say, fairness and bias is similar but slightly different than how it could be used to address explainability. Shall I continue? So counterfactual data augmentation is where counterfactual instances are constructed and incorporated into the training data. So this method works both for invariance and sensitivity. For instance, with invariance, it is possible to add a term to the learning objective that penalizes disagreements in predictions for counterfactual pairs. So a sample with a causally irrelevant characteristic Z is paired with a sample that has the counterfactual Z characteristic. And if we were testing for sensitivity, the intervention would be on the label Y, and we would augment the training data with label counterfactuals. As in, we would pair a sample with outcome Y with another sample labeled with the counterfactual of Y. Research has shown that data augmentation should reduce sensitivity to noise and improve out-of-domain generalization. So there are several ways to generate counterfactual examples. This is manual post-editing, heuristic replacement of keywords, or automated text rewriting. So the first option of manual editing is usually accurate, but it is expensive. The second option of using keywords only works in some scenarios. For instance, when counterfactuals can be obtained by making local substitutions of words like pronouns. This keyword approach, however, does not always work. There are no guarantees that it will have coverage of all labels of interest. And this approach also does not generalize across languages. The last option we have is a fully generative approach. So this should confer the advantage of manual editing with the ease of the keyword approach. That is to say, an automated approach should ideally have the accuracy and coverage of a manual approach combined with the speed of a keyword approach. For all three options, however, there is a risk of introducing spurious correlations. So for example, if we use a keyword substitution approach, this may introduce new spurious correlations if the keyword lexicons are incomplete. The substitution rules may actually be taken up as correlative predictors, which will of course be spurious. The other two options of manual editing and automated text generation, they share the same issue where the generation of counterfactuals can also introduce new spurious correlations. So consider how annotators will generate contradictory statements in a natural language inference dataset. So generally, an NLI dataset will have three classes: neutral, entailment, and contradictory. However, it is human annotators who have to create the contradictory statements. They may use repetitive negation words that will present as a correlative pattern during training. In essence, data augmentation uses counterfactual examples to directly address the missing data issue inherent to causal inference. However, as a caveat, this approach is vulnerable to spurious correlations. So we're going to move on to talking about fairness and bias, and we're going to start by talking about protected attributes. When it comes to ensuring that models are fair and bias-free, Causality provides a language for specifying desired fairness conditions across demographic attributes like race and gender. For instance, a study from 2016 showed that a causal analysis was required to determine whether an observed distribution of data and predictions raises fairness concerns. They discuss how anti-discrimination law requires AI models that will not perpetuate existing inequalities. And this work generally focuses on protected attributes such as gender, race, and religion, amongst others. This idea, however, of fairness through unawareness would suggest that AI models simply need to ignore such protected attributes. However, this particular study claimed that it's ineffective because of redundant encodings, which make it possible to predict these protected attributes from other features. So research done in 2017 showed that a fairness metric can be motivated by causal interpretations of the data generating process, or DGP. They essentially define a concept of counterfactual fairness, where a predictor is fair if for each individual, prediction remains the same for a counterfactual version of the individual that is created by changing a protected attribute. In other words, if a prediction is invariant to a change in an individual's protected attribute, then the predictor can claim counterfactual fairness. So this is necessary since historical data can contain biases based on these protected attributes. So AI models need to account for this and avoid being discriminatory. In a similar vein, another study, also from 2017, used causal inference to develop a framework for model fairness. This framework was supposed to capture the intuition that a decision is fair towards an individual if it is the same in the real world as it is in a counterfactual world where the individual belonged to a different demographic group. So that is to say, changing a protected attribute, such as race, should have a counterfactual invariance in prediction. There have been questions about the legitimacy of treating certain protected attributes as variables that can be subject to counterfactual reasoning or intervention. A person cannot actually change their race or sexuality, and while gender and religion can change, the ethical question becomes whether we should be treating them as something that can be intervened upon. As a solution, some researchers have suggested that observable proxies, such as names, could be used to test for invariance. Counterfactual data augmentation has actually also been used to reduce bias in the pre-training of models like BERT. However, the extent to which biases in such pre-trained models will propagate to downstream applications, this remains unclear. But essentially, the role of counterfactual data augmentation is to reduce the model's reliance on spurious correlations for predictions. So again, not being right for the wrong reasons. So currently, NLP models like BERT act as inscrutable black boxes, which means that they are difficult to explain, and interpreting the results is not a clear process. Therefore, there is a need to be able to diagnose errors so that decision makers can trust the results. This means that there needs to be both explainability of the method and interpretability of the results. At present, a common approach is to exploit network artifacts such as attention weights to generate explanations. The justification is that attention weights are computed along a path to generating a prediction. An alternative approach is to attempt to estimate simpler and more interpretable models by using perturbations of test examples or their hidden representations. But both of these approaches, attention and perturbation-based, have important limitations that can make them misleading. For instance, research has shown that attention-based explanations are generally only possible for individual tokens, and therefore cannot explain predictions in terms of abstract linguistic concepts. This means that if it is the writing style or the topic that is having a causal effect on the prediction, then paying attention to individual tokens cannot tell us why a prediction was made. There are two issues with perturbation-based methods. Firstly, perturbation of test examples do not allow for estimating the effect of sentence-level estimates. And secondly, this process will often generate implausible counterfactuals. Luckily for us, though, it is possible to use sensitivity or invariance as a way of interpreting models. There are far more invariance approaches to interpretability than sensitivity, but both types of interpretability measures will be discussed next. Starting with sensitivity, the goal would be to generate counterfactuals with the minimal changes needed to obtain a different model prediction. So a sensitivity approach would improve explainability since it will highlight the changes that are required to change a model's prediction. Researchers who have focused on generating counterfactuals to improve explainability claim that it is not only necessary to create plausible counterfactuals, there must also be a diversity of counterfactuals. Counterfactuals can also be used to identify invariances. One approach would be to generate counterfactual examples using data augmentation, and then compare the prediction for each sample to the prediction from the example's generated counterfactual. Another invariant approach would be to try to improve the interpretability of models by using contrast sets to evaluate a model's decision boundary. That particular study suggested that after a data set is constructed, the author should manually perturb the test instances in small but meaningful ways to create these contrast sets. So these contrast sets should ideally provide a local view of a model's decision boundary, which can then be used to more accurately evaluate a model's true linguistic capabilities. However, despite the progress made in generating natural language counterfactuals, For abstract linguistic concepts such as style or topic or sentiment, it is often not possible to generate meaningful counterfactuals automatically, and it is too expensive to do this manually. Given this issue, an alternate approach was proposed where the text itself is left alone, and instead the representation of the text is manipulated. So an example of this approach is to use a counterfactual language representation model. A study showed that it was possible to compute counterfactual representations by pre-training an additional instance of a language representation model like BERT with an adversarial auxiliary task that controls for confounding concepts. So in essence, the study created a counterfactual version of BERT and used the comparisons to aid in interpretability. Overall, incorporating invariance and sensitivity tests into the model development process is a way of using causality for greater interpretability and explainability. Thank you everyone for lasting the whole way through. This brings us to the conclusion, and thank you for participating. I wanted to take a moment again to acknowledge the inspiration of the survey paper that I referenced several times. I hope that this talk has inspired some of you to think differently about the NLP models that you use for work. And perhaps some of you might decide to try using counterfactual data augmentation to improve your models. As promised, here are the resources. I do encourage anyone who is interested in these topics to check out some of the books and papers listed here. And finally, just thank you for listening. I hope this was interesting. And if anyone has questions that they didn't get a chance to ask, please feel free to connect with me on LinkedIn.
Thank you, first of all. And yes, as you said, everyone who has questions and even questions which have not been answered yet can contact you on LinkedIn as well. So that's how we actually got in touch again. I have a question from Brandon. Brandon, I would like to put you here to ask the questions directly, if you like. You have your allowness to speak. Brandon, can you? Yep, here we go.
Yes.
Hi.
Yeah, I was just curious. So with counterfactual data augmentation, that would be like swapping one word for the opposite word, right?
Not exactly. There are a few ways to go about it. So I think what you're talking about there is the keyword-based approach. And it could work, for example, if we were just applying this to pronouns, like we wanted to make sure there was no gender bias. So every time there's an instance of a text where it's referring to a man, you could switch all the references to a woman and see if the predictions are invariant to those changes. But keyword approaches won't work for all situations. That's why manual editing is at this point the best option, because automated text rewriting hasn't yet gotten to the point that we can sort of replace the humans in this process.
Okay. Yeah, I guess, yeah, my question was just related to that keyword approach. I was just wondering if you could, instead of swapping things out for the opposite, if you could just instead put in a generic term for both, if that would achieve the same result.
Sort of like masking tokens in a sense.
Yeah, just like a token for race or for gender or religion.
I would think that we would have a similar issue where, if we were to try to just ignore protected attributes, that in some ways that's already in the data and it will come out through other factors, whether or not we include race in the data set, it's possible to predict it using some of the other features. So similarly, if we were to just eliminate all mentions of race from a text, it wouldn't necessarily mean that we would be eliminating bias against race in that sense. Does that make sense?
Yeah, I think so. Okay. It sounds like the keyword approach is pretty limited.
Yes, and also because of just like, it doesn't generalize well across languages. And as I'm sure like many of you have to like deal with data sets where there are multiple languages. So that can also be tricky.
Okay, yeah, thank you.
Thank you, Brandon, for bringing up a question. Hold on a second. Yeah, coming back to one of the questions in the beginning. So I know that sometimes people are quite curious about, is there any kind of code? Do you have real code examples somewhere on a blog or so, which people can just dig deeper into?
So I don't actually have any code examples specifically for this, but the one thing I'd like to direct people towards is there is this automated generation framework called Taylor that was introduced, I think, relatively recently. And this is an attempt at like automating the process of generating counterfactuals using perturbations. I myself haven't actually tried using it, so I can't like vouch for the quality of it. But at the moment, people are trying to take steps towards automating this whole counterfactual data augmentation. And Taylor, as in like, sewing things, that is the one that I've run across that seems to be promising.
Thanks, awesome, for all the tips, Haya. That's very helpful. Looking at the chat and the feedback we got, so it was like a note, great presentation. Thank you for sharing your knowledge and helping us think about this work in a new way. Good examples, thanks. So one feedback. And Marina also said it was a great presentation. Thank you. Looking at the time when you're actually in your lunch break, yeah, so it's just spending the time with us, which is just awesome. I will again say thank you to everyone who attended today. And listen, this was highly, very condensed, very intense talk, I have to say. And this was awesome. And it was recorded. So anyone who just thinks, can I just watch it again? Yes, of course you can. To get to repeat things you might have lost at some point. We were going to upload it on YouTube again. And I want to say thank you for everyone who attended. And Haya, again, thank you for just taking the time and preparing everything and being so patient with us.
Of course. Thank you for having me. I've enjoyed this experience. I enjoy talking about NLP, so this was fun for me.
I think it was fun for us as well. I think it's up, like Peter mentions, many things. I guess I have to replay a few seconds or sections. I do think so too. I think many things is like, okay, I need to rethink it. What was it like? I'm going to repeat it myself. So thank you again, and I wish everyone a nice day, nice evening, whatever time it is on your side. Haya, it's still daytime for you, so there's a lot you can enjoy today. I hope you find nice people, whatever. Thanks again, and say goodbye. See you next time.